All right, so welcome back. Today we're going to continue with lists and list-based data structures. Last time we looked at array-based lists, where you had a list, data structure, and encapsulated inside of it was an array, and that's why we called it an array-based list. What we're going to doing now today is we are going to be looking at linked lists, which are a fundamentally different way of representing a list and representing data. So remember that we are on Piazza. If you've got any questions, go ahead and post there. Otherwise, what is a linked list? I've got a visualization here to show you what it looks like here in a second. But before we do that, let's go ahead and talk about, in general, what a linked list looks like. So a linked lists, right? So a linked list is that it doesn't have an array. There's no underlying array. Instead, elements are stored inside of individual nodes. Right? These nodes have, of course, a reference to the thing that you're storing, but they also have a reference to another node, right? Each node references its element and the next node. All right, there you go. And that, by doing that, what you can do is you can link them together, which is why we call it a linked list. And here's the visualization over here. This is a pre-prepared linked list. We have some terminology here to discuss, though. The start of the list is the head of the list, and the end of the list is the tail. So it is oriented one way. Usually we draw it left to right, but of course, inside a computer, there's no real left, right, up, down, whatever. Right? There's a first element, and then there's a last element. So it is ordered in that sense. It's not necessarily sorted, though. We've got 22, 2, 77, et cetera in this list. Clearly, it's not sorted, right? The beginning of the list, you start at the head, and then what you do if you want to access each individual element, you need to, instead of jumping to an index like an array-based list, you have to traverse each node. So, for example, if I want to search, all right, let's search for 43 here. 43, and here's the visualization. We start at the head, and this is not it, so it's going kind of fast here, but that's okay. I can replay it if you want to. We started at the head, and then that's not it. We looked at the element that was stored inside of that node. That's not what we were looking for. We were looking for 5, remember. Or, sorry, 43. 43, right? So we started at the head. 22 is not equal to 43. Okay, go to the next node. 2, that's not it. Go to the next node. 77, that's not it. 6, that's not it. Go to the next node. 43, we stop. We found the first element that we're looking for. Now, of course, there are variations on this if you wanted to find all the elements that matched your search criteria, or the last element, right? Then you have a little bit different behavior here. But that's basically how you use the list. Instead of jumping to a particular location like you do with an array, you have to traverse the list starting at the head every single time, right? So it's kind of like rewinding a tape, an old school, cassette tape or something. If you want to listen to that song again, you're going to have to go all the way back to the beginning or whatever, right? Beginning of you're going to have to rewind it, okay? That's the visualization right there, okay? So each node is chained together. Each node is chained or linked together, and that's why we call it a linked list. Together, sorry. Each operation, each basic operation, involves traversing the list, right? So traversing, again, is not like an array where you can, I want the 10th element. Okay, just immediately jump to index 9. The way that works with an array-based list at least, is exactly how it would work with an array. With an array, everything is stored contiguously. So here's the first element, here's the second element, here's the third element. So that you know because the first element is at some memory location, you know how many bytes each one takes. All you have to do to jump to a location is to simply do some math. Take this memory location, and I want the 5th element. So 5 times however many, 4 bytes for each integer, that's 20 bytes away. So this memory location plus 20 bytes, and I jump to that memory location immediately. We don't have that luxury here. Instead, we get different advantages from a linked list. Right? For example, if I had an array-based list and I wanted to insert something at the head, at the beginning of the list, what would I have to do? I would have to make room for it by shifting everything down. Do I have to do that with a linked list? No, what would it look like? So let me go ahead and, how do I shut this off? Here we go. I've got to bring this back over here. Let's go ahead and insert. Insert at the head. In other words, at index 0. We'll go ahead and insert the value 42 there. Right? What does that look like? What does inserting a new node look like? Well, first of all, you have to create the node. So I create this node, and I put 42 in it. Now I've got 42 right here. I want to insert that at the beginning of the list. So what I'm going to do is I'm going to link this in, just like if I had a chain, 4 items here. I put in a new one up here, and I chain this one to this one. But then I also need to update my head reference, because this becomes my new head. So visually, what does that look like? Create a new node 42, link it to the old head, update the head reference to this new node. What does inserting at the tail look like? Insert at end. With an array-based list, all we had to do was jump to the end and put it where it belongs. We possibly had to expand the array, right? Expand or contract the array. I don't have to do that here, though. If I can get to the tail, all I need to do is create a new node and link the old tail to this one. So let's do that. Let's insert at the tail. And here I'll go ahead and do 101. There we go. Oh, I can't do 101. It says only a value between 1 and 99 for this visualization. Probably because they wanted to keep it at 2-digit numbers so that it fits in their small little nodes there. So give me your favorite number. 28? Oh, okay. They suggested one. Thank you. All right. Well, here we were able to jump to the tail as long as we kept a reference to the tail, right? As long as I have this node tail and everything that came before it, I don't care about that stuff because I'm going to add a new tail, make the old tail point to this one, and this one becomes my new tail, right? 28 becomes the new tail. What does it look like if I insert something in the middle, though? What if I wanted to do 0, 1, it's still 0 indexed, so the first element here, 42, has an index 0. Even though we're not indexing anything, it's still helpful to think about it as an index so that you can think of the first element at being at index 0, 1, 2, 3, 4. So what if I wanted to insert it right here at 77? So I'm going to shove 77 over to make room for it. I don't need to do that because it's not an array. All I need to do is create a new node, link the, and I want to insert it into a chain, break that chain, make this chain point to the new node, and make the new node point to the old chain. So if I'm going to insert at, say, 0, 1, 2, 3, index 3, let's put in 90. Right? Well, that involves getting there, right? Traversing the list to where you want to be, creating a new node, making it point to the old node, and then making the previous node point to this node. Right? And I can go back a little bit. Let's do it one step at a time here. So again, what I had to do is I had to find that location first. Now here, this is the previous one. This is the one after. I assume that AFT stands for after. We'll go ahead and call it previous and current. Right? I want to insert it between these two nodes right here. So that's going to involve breaking creating a new node, making this new node point or reference to the next node here, and then breaking the chain from the previous and making it point to here. And now you can pull this chain tight, and it becomes a new list like this, right? Or it becomes an updated list like this. Okay? All right, so questions on how that works? Pretty self-explanatory, especially if you think about it as a chain, as a bunch of links in a chain. If you've got a chain that's 10 feet long, right? And you want to make it 10 feet and 2 inches long. Well, you just need to add a new link into it, right? Well, if you want to add it in the middle or at the end or whatever you want to do with it, right? So with that understanding, let's design our own linked list, okay? So what is this going to look like, first of all? Should I have an array inside here? Should I immediately jump to I want an integer array, private int elements. That kind of defeats the purpose, right? What are we keeping track of over here? What's the only thing that has, if I always have to start at the beginning of the list, that's what I need to keep track of. I need to keep track of the head, right? So let's go back over here. It's not going to be an array. It's going to be the head. Now, is this going to be an integer? Remember that these nodes here, they contain an integer, but then they also contain a reference to the next node. So what is this telling you? I probably need another way of representing two things. Right? If I've got a concept of a node that has an element and a reference to the next node, I've got more than one thing. What should I be doing? Wrapping it up in a class. So let's do that. Let's go ahead and create a node class. Right? And I'm going to learn my lesson from last time. Last time, remember that we started out with a simple list that kept track of not generic elements, but an integer list. We decided at the end that's only good for integers. What about doubles? What about strings? So we went back and refactored it so that it was parameterized, so that it could hold any element of type T. I'm going to take, now that I've learned that lesson, what I'm going to do is I'm going to design this from scratch with that idea in mind. This node, what does it hold? I don't know. I don't care. Right? It just holds stuff. So I'm going to parameterize it to be T, right? And private T, in fact, I'll make it final, T element. Right? So I'm making it private, good encapsulation. I'm protecting it from the outside world. I'm making it final so that my node class, at least with respect to the element, is immutable. And what type is it? It's T. Right? It could be a double. It could be an integer. It could be a string. It could be whatever. It could be a bank account. It could be a sale. Right? Okay. What else do I need? I need a reference to the next node. So private next. What should be its type? An integer? Or T? Right? A node referencing another node. What should it be its type? A node. Also parameterized on the same type. Because you don't want the first link to be an integer and then the next link to be a double. That would be like mixed types or something like that. I guess you could do that if you really wanted to. And then I'm holding different things in my linked list. Sometimes I'm holding, the first element is an integer, the second element is a double. I don't want to think about that kind of world. All right, I'm not making this final because I want to make this a little bit more versatile. Remember, all of our operations here, I am sometimes changing what the next element it looks like, right? Sometimes I'm going to say, okay, I don't want you to point to that element anymore. I want you to point to this element over here that I just created so that I can insert a new link into the chain. Right? So I'm not going to make that final, okay? But I do want a public node T element, and then this dot element is equal to element. There we go. And now it stops complaining because I've actually set that final element. What else might be convenient in this class? Just think about the node itself, right? We're building this. This is basically bottom-up kind of design, where we're focusing not on the list implementation as such. We're focusing on the node implementation first. And that way we can take those building blocks and add them together for a larger list implementation. What would be convenient with a node? A what? A set node. So in other words, set the next element, right? So I'm going to go ahead and go up to source here and generate getters and setters because I don't like writing code by hand, right? So maybe get element. Why is there no set element? Because I made it final. It's immutable. I like that. Of course, if you put something into the node, you'll eventually want to take it out, right? Because you want to access it. Get next. And even set next, because sometimes I want to change it. So I'm going to go ahead and generate all those things. Nice. What is the default value of next right here? This dot next is equal to what? If I don't specify, what should it be? Conceptually, I don't know. And I don't know in code is null, right? Now that's the default anyway, so this is kind of superfluous code, so I'm just going to go ahead and get rid of that. Right? That's what it's doing by default. Now, what does it mean if I've got a node that points to null? What does that mean for the next? Give me the next. Oh, okay, here you go, null. What did I give you? The end of the list, right? Or at the very least, if it's just a node, then it doesn't have a next, right? So maybe it will be convenient to have a public Boolean has next that returns no. You don't. Before you ask for it, does it actually exist? No, it doesn't. It's null. Or yeah, it does exist. It's non-null. So here you go. Here's your next node, right? And the get next here is actually returning a node. Okay. It's not returning the element in the next node. So what would the logic be here? If this dot next is equal to null, then does it have a next or not? Return false. Good. Else, return true. Not else p, but else return true. And that's pretty clear code, right? That's if it's null, then we'll go ahead and return false. Otherwise, we'll return true. But if it's a true or false kind of thing, is there a way that I can simplify this code? When does it have a next? When does it have a next? So let's state this positively. When this returns true, right? This is true when this dot next is not equal to null. That sounds like a much better way of doing this. Return this dot next not equal to null. That's just an expression, right? That's much simpler code, right? Now, readable, more readable, less readable. That's going to be 6 of one, half a dozen of another. Right? You're going to argue back and forth on that all day. But I do see a lot of code out there that can not necessarily. I would accept either one in this case, since it's simple and readability is more important. But I see all the time superfluous code of if this expression is true, return true, else return false. Right? That's the kind of code you don't want to get in the habit of writing. Right? It's really superfluous. Okay. That's good for our node class here. Now, what does my linked list look like now? The head is a node of what? Integers, doubles, strings. We also should parameterize my linked list so that it can hold, so that the answer to all three of those is yes. Right? Whatever you want. Now, you could also optional, right? Private node t tail, right? The end of the list. If you want to keep track of both of these things like this visualization does, should I keep track of the second and the third and the fourth and the fifth? What would that end up looking like? If I wanted to keep track of all the nodes, it would be a node t all the nodes, and we'd have an array. We're back at square one, right? If this is what you're shopping for, then this is what you want over here, right? No, that's not what we're going to do. We're not going to keep track of all the nodes. We're only going to keep track of the head, okay? Now, what should the constructor look like? Public, my linked list. I'll just make the default constructor here. This dot head. How do I make an empty list? Let's visualize it over here. Create empty. What does it look like to you? Nothing. Not even a single node, right? So in Java, in terms of Java code, what does that look like? This head is equal to null, right? And when I insert something new, then at that point I create a new node and make the head reference it, right? Now there are variations on this where you can have what are called sentinel nodes. where you have this kind of dummy sentinel node at the end that always exists. And it's a non-null value. It's just this very special value that flag value that you point to. Initially, you could point it to that and not have to use null at all. But yeah, it's an internal thing. It's a sentinel node. It doesn't hold anything. It just is there to indicate that that's the end of the list. Right? But let's go. That complicates things, in my opinion. Let's just go ahead and go with this. Right? Okay. Well, if you've got a list, you might also want. What else did we do over here in this array-based list? We had increase. Do we need increased capacity here? The capacity is infinite. Just create a new node, right? Get element at index, okay. Add element at index, add to the end, add to the start, size, index of, we did that in the other section, and a toString method. So let's go ahead and do all of that. Eventually we'll get to them all, but let's do that in the context of a linked list, okay? What do you want to start with? Let's start with something simple. All right, add to, what do I call it over here? Add to start. Right? Oops. All right, add to start. An element t, and we'll call it x here. Obviously, we don't have that here. Right? So add to start. If I start out with an empty list, and I insert, say, 42. Let's go 42 there. What does that mean? I create a new node, and I make the head point to that node. But that's only if it's empty, right? And the tail is also the same. The head and the tail are the same thing because there's only one person in line. The head of the line, the end of the line, but some people call it the tail of the line, right? The head of the snake, the tail of the snake, right? Or whatever animal you want to think of, whatever your spirit animal is, right? So, hopefully they have tails, otherwise then you'll have to choose a different spirit animal to think about. All right, add to start. Let's check. If it's empty, then I simply need to create a new node and then make the head point to that new node. Right? So if empty, then I will create a new node, node t, right? New head is equal to new node containing the element x. Do I need to worry about the next yet? Not if it's empty, right? Just like I didn't over here. Right? If it's empty, and then this dot head is equal to the new head. Else, it's not empty. That means we've got a situation that looks like this. Now we could have like 50 things trailing off of this if we really wanted to. I'll go ahead and do that with a create random, right? So now I've got 4 things hanging off of this. If I wanted to insert at the head, what do I need to do? What operations do I need to do? Now I need to insert 42 at the head. Go. That means creating a new node, making it point to the old head, and then making the head reference point to this new node. And you note that the order was important there. You had to create it, of course, before you can work with it. Then you make it point to the head. Then you make the head reference update to this new node. Why is that important? What if we did it the other way around? Here's, unfortunately, I'm not going to be able to do that here. What if I made the head reference 42? And then I tried to make it point to the old head. I lost the reference, exactly. Right? Now, if I saved it off into a temporary variable, that'd be fine. But then you're doing more work for the same thing. Right? Just go in the correct order. So, if it's not empty, I still need to create the new head. I make the new head dot set next equal to the old head, which I've not changed yet. And then finally, I say this head is equal to the new head. Okay? Now, that's a little bit different here. Empty or not empty. And I haven't taken care of, well, actually, let's take care of this before I simplify this code. How do I tell if it's empty or not? Is what? If the head is null. If this dot head is null, then I know that it's empty. Wait a second. Determining whether or not a list is empty. That seems like it's convenient, right? That seems like it's useful. That seems like it's functionality. Maybe I should be putting that into a function. But that's only one aspect, right? What if it's empty? Or what if it's not empty, right? Empty, not empty. There's missing information there, right? Say that it's not empty. What else would you want to know? How big it is, right? Just like we did over here in my list. We kept track of the size. I'm going to do the same thing up here. Private int size. And the size is initially 0 because you haven't put anything into it yet. If I add it to the start, now what I can do is have a convenience method. Public Boolean is empty. What's the condition for this list being empty? Now, before it was, is the head null? But now what can I do even more conveniently, or not conveniently, but a little bit easier to think about. This list is empty if there are 0 elements in it. Right? You don't even have to think about null or heads or anything like that. Return this dot size or size. If it's 0, then it's true. Just like I did before. If it's 0, then that's true. It's empty. If it's not 0, then there's something in it. It is not empty. Right? If it's 0, it is empty. I think I misspoke there. Right? Well, it should. Wait a second. I also want the outside world to know how many things there are. So let's go ahead and put in a getter there. Public int get size. There we go. And return this dot size. Right? How many elements are actually in there? To do later, put documentation on each one of these non-trivial methods. But now that gives me pause. Before I said this dot size, I could go this dot get size, right? Stylistically, 6 of one, half a dozen of another, right? Unless there is like some inheritance where this is an overridden method and then you have to pay attention to it, or you plan in the future to inherit from this class, then you should be using the method rather than the variable. But whatever. Right? All right. Now I can change this. Now I can use that is empty. Now if it's empty, then I have to create a new head and make the reference point to this new head, et cetera, et cetera, et cetera. But I'm using something that's closer to English now, right? Rather than saying that thing is null is my condition. Put that into a function, name that function appropriately, and it makes it a lot more readable code. Okay? No questions so far, and we are good on our stream. Good. Now, this code does not seem too different to me, does it? This line is exactly the same as this line. This line is exactly the same as this line. The only difference here is this line. Now, if it's not empty, then the new head that I just created will be pointing to the old head. But if it's empty, what if I did the same thing if it's empty? What's the old head? If it was empty? Null. So you're going to make it point from null and change it so that it's pointing to null. Okay. There would be 0 difference there. Right? And if there's 0 difference, then why do we have this condition at all? Right? Let's simplify this. There. Now, of course, I'm not going to get rid of these just because I'm not using them now. I could be using them in the future. They're still convenient, and I could be using them outside the class as well. Okay? Let's test it. My list is no longer a list. It's my linked list. There we go. There we go. We have not done the toString method yet, so we'll have to think about that. Add to start. And then we'll print it out here. The rest of this stuff I will go ahead and temporarily comment out because it's not compiling. When I run this, of course, nothing. It's going to print out this mysterious string, which again is the fully qualified package name and class, along with the Java virtual machine memory address. Not too helpful. So let's come back over here to my linked list, and let's get a visualization of this by using a public string toString. Well, this is going to be our first traversal, right? What does it look like? And let me go ahead and finish this out. What is it going to look like to print this out? And there is no print function here because it's right there in front of you, right? But that's what we want. That's what the code that we want to write to get that visualization. 42, comma, 15, comma, 86, comma, 78, comma, 32. What am I going to have to do? I'm going to have to traverse this thing. Start at the beginning, get the element out, print it. Go to the next one. Get the element out, print it. Start at the next one, next one, next one, next one, next one, until when? You get to the tail, pull that element out, print it. When do I stop now? What? If it's null, right? When I get to the tail, I know that that's the end because the next node is null. In other words, it does not have a next, right? All right, let's go ahead and create a string builder. Because I'm not actually going to print them out. I'm going to append them to a string, and then that's what we'll eventually return. Okay. All right. Maybe if it's empty, I want to print out a different message. So if this dot is empty, nice, and now I am using it, right? Then sb dot append, just a special message here, empty, right? Instead of, I like doing something positive, even if there, normally if you would print this out, there's nothing in it. So either square brackets, empty like that. I'm putting this actual message empty in there. But I don't like to see, blanks, because then if you just see a blank, then how do I know that something went wrong versus there's actually not anything in there, right? So let's give positive information, positive feedback that in fact it is empty. Else, there. Now I'm going to start at the head. Here, I'm going to keep my cursor here as a finger. Start at the head, get the element, print. Go to the next. Go to the next. Go to the next. Go to the next. Right? I wish I had a finger cursor here. Right? In other words, I'm keeping track of these things with a reference, with a current node. Node T current. Where do I start? At the head. Okay. Now, what's my condition for continuing? While, well, I've already created a variable called current. So let's think about it in terms of current, right? I'm pointing at 42 right now. Next, 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 next. If I go to the next, then the current node is null, right? So you could change it so that you start before the list. While it has next, then go to that next. While it has next, has next, has next, has next. Oh, it doesn't have next, so I stop there. So I'm just shifting the burden one step behind instead. So while the current is not null, that means that there is something to process. Right? So get the element, or append. I don't even need to document that, but sb.append current.get element. There we go. And now I need to set myself up for the next iteration. If this is my current, I need to update what my finger is pointing to the next node. I need to move it over here. So current is equal to current.getNext. Nice. Right? When do I break out of this loop? Current, 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 not null, not null, not null. Next, now it is null. Right? So We could go back and shift this by 1 and then use the has next. It's a little bit tricky because then at the beginning, what if it's, you have to set it to, you have to ask, is there a next with respect to the beginning of the list, right? And that's going to be an if else and then a loop. And simpler code is always better. Right? So let's go back over here to the demo. Remember, I'm inserting at the beginning, so I insert 10. Then I insert 20. Then I insert 30. So what should the list look like after inserting 10 through 100 by increments of 10? What's going to be at the beginning of the list? Uh-oh. Empty, empty. Same problem I had last time, right? Why is it empty? It's always saying that it's empty. That's because the size is always 0. What did I not do? This dot size plus plus. Plus. There we go. Okay. Let's try that again. There. Aha. Ugly. 190, 80, 70. So let's go ahead and fix that a little bit. So what should I be appending? Let's add a comma and a space to make it look nice. Somewhat nice. Of course, there's still that trailing comma. If you wanted to change this so that it printed nicely, that without that trailing comma, you have to stop short, right? You have to detect not only is the current next, but does the current have a next? And if not, then no, you would need to detect, is the next one the last one? So in other words, is the next one, does that have a next, right? I don't want to get into that right now. But you can go ahead and certainly fix that with your implementations if you do choose to do a linked list implementation. For the last phase is what I'm referring to. All right, we've got at least this insert at the head functionality. What other functionality do we want? How about getting an element at a particular index? All right, let's do that. Let's see. There we go. Get element at a particular index. Well, because I'm keeping track of the size, I can go ahead and throw this exception if you ask me for something that doesn't exist. Right? And so I'll go ahead and keep that. But I can't, just like with an array list, an array-based list, I could immediately jump to where you want because we have random access. That's what that's called. Random access means that you can, if you have got a memory address where everything begins, everything is contiguously stored, one right after the other, and you know how many bytes each one takes. All it is math, and you're going to an offset, right? Jump to memory location, whatever. Right? And it's pretty cheap and easy. But here, we don't have that luxury. What does it look like if I search for, say, 86? And we're not going to have like an index-based search example here, but we'll search for whatever element is at index 2. So start at the first, 0, 1, 2, we're there. We're done. Here you go, 86. Right? So what does that look like here? Kind of like what we did with this down here. I need to keep track of a current, but instead of checking, am I about to fall off the edge of the earth, what do I need to do? Start at the head and a for loop. Well, yeah, so with a while loop, you know, I just kept going. I did know how many things there are, so I could have used a for loop because I'm keeping track of the size, right? But here it seems more natural to use a for loop. For int I equals 0, I is less than index I plus plus, right? Now instead of using I as an actual index, because I don't have an array here, all I'm doing is go to the next, go to the next, go to the next. This dot current is equal to current dot get next. Now let's think about this. For an index base of 2, 0, there are 3 elements in there. In fact, let's do it on this one, right? Just like I did here. 0, next. 2, 1, next. Oh, I guess I did 0, 1, 2. 0, 1, 2. I guess I did 1. Okay. Now am I where I need to be? Basically, I'm asking, is this correct? Do I need to go less than 1, more than 1? Well, we could think about it and whiteboard it, or we could just simply test it, right? So, return this dot current, or sorry, not current, current dot get element. I don't know. I think it's correct, but we'll find out here in a second when we go over to the demo to get that element. So int x is equal to L dot get element at index, and let's go ahead and go with 1. So here my list is different. Here it's 0, 1, 2, 3, 4. Let's get the element at index 4. What should we expect there? 60. System.out.println x and 60. Should I also test? What else? 0, okay. Get element at head, right? 100, good. What else should I test? Edge cases, corner case, literally edge cases here, right? You're at the edge of the list. 10, okay. You could also test your error conditions. You ask for something that doesn't exist, throws an exception, that's good. Or you could even go into a, quiet Siri, for int I equals 0, I is less than L dot get size, I plus plus. This is only a visualization, but I would expect it to have the same output as the, well, 1 to a line, but the same output as the toString method here. 100 down to 10. Ooh, wait a second. That sounds like very, very similar functionality. What if, I've got a bright idea now. What if I come back over here and I change this so that I get the element at 0, print it, or append it. Get the element at 1, append it. Get the element at 2, append it. Now we're back to the old painter paradox. So I think I've told this story before, but do you remember the painter? Here's the story. This will come up later on when we look at algorithms and algorithm analysis, but somebody hires a guy to paint a fence, and he pays him by the hour. And so the first day he makes pretty good progress, right? He starts at the beginning of this fence, and he's painted 10 feet. Okay, great. He's doing a great job. I'm going to come back now. But at the end of the day, he's not much farther from where he began, right? And so he goes, oh, okay, maybe just took a break or something like that. Fine, I'll pay you for another day. Comes back, even less progress has been made, right? Why? And so he says, show me how you paint. And he goes, oh, okay. So he starts at the beginning of the fence, dips his paintbrush, walks all the way over to the unpainted portion, and then starts painting. Once it runs out of paint in the brush, he has to walk all the way back to the beginning, dip again, walk all the way back over to the fence, and continue, right? In other words, one paint stroke or whatever it takes means that he's walking back and forth. Now at the beginning, he's only walking back and forth a few feet. But towards the end, he's walking back and forth a big distance. Right? That's what's happening if I did it like this. Let me go ahead and show you what it looks like. For int I equals 0, I is less than this dot size, I plus plus, sb dot append, and then we'll go ahead and get this dot get element at index I. Right? It looks pretty innocent, but you have to understand the underlying data structure here to realize that this is a terrible idea. What if there are 1 million elements? To get that last element, you're going to have to start at the list and traverse all the way to the end to get it. What if there are 2 million elements? You're now doing million traversals back and forth just to get to the first element after the millionth element. Right? This has quadratic behavior. 1 million times 1 million operations to get all of the elements. What's 1 million times 1 million? A lot of zeros. At this point, I like quoting one of my favorite movies, Once Upon a Time in the Old West, where the bad guys, the kind of bad guys, are discussing that that land is going to be worth a lot because the train's coming through. So they said that's got to be. The first guy says it's got to be worth thousands of dollars, and the second guy says try more like thousands of thousands, and he goes, we call them millions. So what is the millions of millions? We call them quadrillion. Trillions is 1 quadrillion, I think it would be. It would roll over because 12 zeros, or whatever it is. That'd be quadrillion, I think. But we call them quadrillions, right? So 1 quadrillion operations just to print a list of 1 million elements? Nope. I can show, in fact, I can demonstrate it right now. All right, let's go ahead and change it over here to the demo. Instead of going up by increments of 10, we'll go up by increments of 1. And we'll go ahead and start at 0, and we'll go up to 1 million. 1, 2, 3. There we go. I'm not going to print it yet. Let me run it. Blink of an eye, just like you expect from a computer. Let's try to print it now. That red stop sign means that it's still going. Do not expect this to execute within a week. All right. We'll let it keep going there. Come back over here. That's a bad implementation. Undo, 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 undo. And it's not just because it's a for loop versus a while loop. Any for loop can, this is a good while loop. You can recode this to be a good for loop as well. So don't think that it's the difference between a for loop and a while loop. It is the difference between the fundamental data structure and how you use it, right? The painter. What should the painter have done? Should have picked up the damn paint bucket, right? And brought it with him so that he wasn't walking back and forth the entire time. This is still going, still going, still going. At this point, I will kill it because, again, it could take hours, maybe days. And let me go ahead and execute this now. And it's still going, but that's only because I/O is expensive, and it's going to slow everything down. Do not kill my OBS. There we go. All right. I/O, input-output, especially to a console, is still expensive. But you saw that it would get done in a few seconds, maybe minutes or so. Right? In fact, if I did this as a... Yeah. It only started because I got done with this while loop. This while loop was done. It would have to be done executing to even be able to get to that point, right? Okay, good. What else do we want? Get element at index, so maybe we want insert something. And what do we call that in our original? Add element at index, there we go. All right, let's do that as well. Add element at index. Give me a bad index, I throw it back at you. Okay. Let's insert an element at, well, 0. If we insert 3 at 0, that's equivalent to insert at head. You could take that as a special case. If the index is equal to 0, oh, you want to insert it at the head. This dot insert add element, add to start, right? Index. Or not index, but the element x. There we go. Else? Okay, that means you want to insert it somewhere else. And by the way, we know that that's going to be a valid location. If it weren't, we would have taken care of that up here. So we're at this point, what do we know? You don't. We know that you want, if you gave it, if it's empty, then the index that you want to insert it at is at 0. That's kind of like inserting it at the head. So it could be empty. There could be elements in there. But what we do know is that the index is valid. Right? If the index is, there are 5 elements in there, then 0 is valid. 1, 2, 3, 4, 5 is valid because that's adding it to the end. Right? If the size is 0, let's see, and the index, add element at index. Yeah, if the size is 0, the index is 0, that's going to be false, right? So we won't throw this exception, right? So there are a couple of corner cases that we may need to think about here. What happens when we insert when there's nothing there, et cetera, right? So help me on this. What's the first thing we need to do? We need to find that location, right? If you're going to insert at, say, index 3, 0, 1, 2, 3. So we're going to insert it right here, shove 86 over. And I'll go ahead and put in, not 42, we've used that, 44, Rizzo. All right, there we go. First of all, now stop. All right. How did I get there? 0, 1, 2, 3, right? So kind of like how we did get element at index. Hey, maybe I could reuse that. Right, so this dot get element at index, and I want to insert it at index. Except that returns what? An element of type T. That's not what I want. What do I want? I want the node itself. Because what I'm going to do is, if I advance this now, I'm going to make my new node point to that old node. I'm going to make the previous node point to this node, and then I'm good. So I'm kind of have to keep track of two things. Just like this visualization is implying, I have to keep track of the previous one and the current one. And I'm going to insert it at the current one by making a new node, pointing it to the current one, and then making the previous one point to this new node. So let's keep track of two things. I'm not going to be able to use that because it doesn't return that type. Okay? Except that, wait a second. I really like that idea. Right? That would have been really convenient, right? Give me the node at that index. Maybe I can break this problem down into two parts. It would be really nice if I had a method that automatically gave me that node and this node, and then I can just, do all the work myself, right? So if it's convenient, if it seems useful, I'd really like that gift wrap to me. Well, go ahead and wrap it up and give it to yourself. Get element at index. Let's not get the element at index. Let's get the node at index. And instead of returning an element of type T, we'll return a node parameterized on type T. We could still have this if you really want to. I'm going to take it out for now, though. And we'll see why here in a second. Now, instead of returning the element, I return current. Right? And that's itching to get. That's me itching to get under the skin right now. That I've got two things that essentially do the same thing with just different return types and different names. What should we be doing instead? We should what? Not parameterize it here, but one should be calling the other, right? Get element at index. How could I modify this? Yeah. This dot get node at index. Still doing the error checking here, and then return current dot get element. No repeated code. DRY principle satisfied. DRY, don't repeat yourself. Right? But still not satisfying for one reason or another. Let me go back over here. Well, actually, let me get rid of this for a second. Return null for now, or we'll just return so that it compiles, right? And don't forget to do. You still need to do this. Right, there we go. But let's go over here to the demo. Now, before I tested, didn't I test it here? Oh, I did here. Sorry. And I'll actually pull this out. Element at index, 4, and system.out.println x. Regression testing, we changed stuff. Did we break anything? The element at index 4 would be 100, 90, 80, 70, 60 still? Oh, never mind. Stop. All right, let's go with 100 again. Or sorry, 10 up to 100. I forgot that I had changed that. And then up by increments of 10. So 100, 90, 80, 70, 60 is what I would get at index 4. Does that work? Oh, there we go. 60 still. Regression testing. We didn't break anything. All right, I'm satisfied. But at the same time, what can I now do? L.get node at index? Node? What the hell is a node? I just have a list. It's called linked list. It's kind of a bad name, and we'll talk, but it's kind of related to this. Right? So should the outside world be getting access to your internal representation? In this implementation where we've got the array here, do we ever leak the fact that we have an array? Oh, here's the array. You can do whatever you want with it. Right? We used good encapsulation and protected it from the outside world. I don't want the outside world to know that there are a bunch of nodes inside, and that's how I'm doing stuff. Right? Here's the node. You can break it however you want. How can I prevent that? Make it private. Now over here in the demo, now you can't do that. Now it doesn't leak that information. Now it's no longer a leaky abstraction because you can't get access to that. I'm closing off the access from the outside world by encapsulating and protecting that data representation. But I now have the best of both worlds. I have a convenience method that I can use to get that element. So which elements do we want? If we want to insert at 3, I think that's what I did, right? Yeah, insert 44 at index 3. Then I did 0, 1, 2, 3. I need the previous. So what should I do? Get the one before it and get this one. Okay, that sounds like a good idea. So node t previous is equal to this dot get node at index minus 1, the one previous to it, and then current will be the element at that index. Another style here, if you've got the stuff, initialization code like that, some people like to align all their equals. Very mathematical, right? If you're writing math in LaTeX, you like all of your equal signs to be aligned, and then they're aligned left and right around those equal signs. Right? I wonder what, nope. I wonder what Eclipse will do to that if I fix it. Yeah, Eclipse doesn't like that. But Eclipse likes spaces around symbols like that. So 6 of one, half a dozen of the other, just be consistent. Who cares? All right, I've got the previous and the current. Now I've got this situation. I've got 15 and 86 right here, and I want to insert 44. What's the next step? Create a new node. So node t, new node equals to new node. Sorry, I'm not that creative. I don't know what else to call this. We could call it node. We could call it u, uvt or uvx, yz, or sometimes used as placeholders. I'll just go with new node. And the element that you are inserting into that node is x. Okay. So I've got the current, aft, the previous, and this new node right here. Next step is make the new node point to the current node. The new node dot set next to the current. Okay. Next step. Make the previous one point to the new node. So previous dot set next to the new node. Do I need to worry about the next node at all? When I pull this chain taut, everything is hunky-dory. Right? Except, what did I forget? Before there were 6 elements in here, and now there are 7. So don't forget this dot size plus plus. Right. Do I need to worry about that up here? Add to start takes care of that for me, so no. And I've done it, so there. There's still a bug here. We need proper testing. We need to come up with a test case that tries to break our code. All right? So, help me out. Let's try some things. L dot add element at index. Well, we'll do it at index 3, and we'll add 42. And then we'll print it out again. So that should be 190, 0, 1, 2, 3. We add it right here, so it'll be 190, 80, 42, and then the rest of it. Oh, switch them around. All right. Actually, I don't like that. I guess that's what we did with the other one, but fine. 42 will be added at index 3. Add element at index. So I guess that's why we did it that way, right? Because in English, it's add this the element at index. So direct object, indirect object. Don't you remember your grammar diagrams? No? There. Uh-oh. Oh, X, sorry. Not print out X. Print out the list again. Now, is it added, just as I said, that's what I said, right? Added at index 3, 0, 1, 2, 3, and all this stuff gets shifted down. It's really not shifting, right? It's just, it's the chain that it was before. I didn't move any of that stuff. I just broke the chain, put something inside in it, and then reattached everything. Pretty cheap, right? Cheap operations. All right, that worked. What's another corner case? Oh, let's add it at the end. Now, there are 10 elements before, 11 now. So if I wanted to add it at the end, it would be at index 11. And let's do something else. 44 was the go-to there. Hopefully they low-balled Rizzo big time, if anybody knows what I'm talking about. Rizzo 44 is Rizzo's number. Anthony Rizzo, first baseman for the Cubs. They lowballed him with a 5-year, $70 million contract, which is an insult. Right? But there, that's what the Cubs did to Rizzo. They treated him like the last person, right? And last in the list. Okay, that worked. What if I add something at index 15? I'd expect an exception, I get that. What if I added something at index -1? I get an exception, and I expected that. What else? Let's go with Bryant. What? Okay, at the start. Oh no, what's gonna happen here? Oh, it worked. Right. Why did it work? Right. I actually was expecting it to break, but let's go ahead and trace it. Why I was expecting it to break is because you're asking for something at I want to insert 17 at index 0. Get node at index 0 minus 1. Let's trace that through this code. What happens when I give it 0 minus 1, which is minus 1? -1. Index -1. For I equals 0, I is less than index I plus plus. So we never advance. Current is equal to the head. In other words, let's visualize it over here. Insert at index 0 and 17. Go, but pause. Go back. Right? So give me the element at give me the node at index 0. That's going to be the head. Give me the node at index 0 minus 1. It's also the head in this case, at least as far as our code is concerned, right? That doesn't present a problem here because previous and current end up being the same thing. Here, let me show you what I'm talking about. By setting a debugger, and let's go through it. There we go. So now I'm at this. I'm going to go ahead and step into. There we go. Okay, over that. There we go. Into. There we go. So let's look at all of our variables here. X is 17. That's the thing I'm inserting. I'm inserting it in index 0. All right, so we'll step over this because it won't throw an exception here. Oh, the one thing that could have killed me by going index -1, I've taken care of as a corner case. If you want to insert it at index 0, we already have something that we know works to do that for you. Add to start, right? And so none of this gets executed, and we saved ourselves by splitting out that special case, that corner case, and dealing with it separately. I'd forgotten we did that, so that's why. I thought I was going to get a nice bug to have to debug live, but we wrote correct code in the first place, in the first try. So always do that. Always write correct code, and then you never have to write a debugger. Right?
Yeah, you never make mistakes. You never need to
Exactly. Erasers are good for other things, though. Right? You can erase stuff off of like a wall or something, like a smudge or something. There are various do-it-yourself projects with erasers or tips, right? All right, let's go back to the Java's perspective here. Still no questions online. Good, still good on our stream. Did we do everything that we had before? Get element at index, add element at index, add to the end, add to the start. We didn't do this one. We could do that one really quick. Add to end. How would you do this? Add the element at index what? This dot size. Right. There are 4 elements in there. 0, 1, 2, 3, 4 is where you want it to be. Very nice. If you solve the big problem, then you can solve all the little problems, right? Yeah.
Would it be good design / doesn't really matter if you have that also be a corner case in the add element at index, where say you want to have the index and you put in the size, then you just call in that function instead, like how we did with the add at beginning.
Like instead of this get size, or
No, like in the function above with add element at index, kind of like how we had handled index is equal to 0.
right?
What if you also did it so that you had like another else if and index is equal to size, and then you call on.
Yeah, it would be exactly like this, though. You still have to go to the end, right? I mean, you could get away with you no longer need a previous anymore. You just need the last one, right? So you'd get away with one fewer call, right? And so you could do that, yeah. Right. By saving multiple traversals, yes. In fact, from a design perspective, I would do that because if there are 1 million elements, go over it 1 million times, go over it another 1 million times, right? Now it's 2 million times. But that kind of red flag tells us that we should be refactoring this. What if I had the previous? How do I get the next? Do I need to be the painter and go back all the way to the beginning and then come back? Do I need to rewind and go back if I've got the previous? How do I get the next? Previous dot get next. Now the painter's not going all the way back over to the beginning. Excellent. Right? And you are complaining because of that. There, now he's not complaining. Right. Okay. Any questions on this so far? Otherwise, what else did we do? Ooh, index of. I don't think I did this in the morning section here. So let's go over this really quickly since we do have time and we can continue it on it next time. Now, let me show you what I did here in the afternoon section. Index of. We want to get the index of an element that's stored in this list. So if we want, we can go ahead and advance this. I want to search for 44. There are lots of ways that you can search for something, right? You can go and, oh, here it is. I found it. Yes or no, right? Yes, it contains 44. No, it does not contain 44. Yes, it contains 44. And here you go. Here's the node for it. Yes, it contains 44. Here's the element for it. Or what's another, what's one piece of information that I can get all three of those other pieces of information out of? What's the index of that element? And if I told you that the index of 44 was 0, 1, 2, 3, 4, then you could get the element at index 4. You could extract its node. You could extract its element. You could do whatever you want with it, right? So index of, here's the key element. Now, with our final version where it was parameterized, we don't know if we don't know that they're numbers. So we're not talking about 44 or 17 or whatever. We're talking about a thing. Is this it? Or I don't know. It's a thing. I don't know how to compare things, right? Is this it? I don't know, right? Is this it? Is this? You need a way of somebody saying, yes, that's the one that I'm looking for. No, that's not the one I'm looking for. And the way that you can do that is through a comparator. A comparator, given two elements, a key element and the current element, can say, oh, they go like this, or they are equal. Right? This one, 17, comes before 44. Or 44 comes after 17. Or 44 is equal to 44. Right? That's what a comparator does. A comparator returns 0, 1, or 0, something positive or something negative, depending on the relative ordering of things. Right? So if we give our class a comparator, then we can do something like that. Right? Now this is, what I'll do is I'll make it this final. Right? And the default constructor here, I want to keep that. So if you don't specify anything, then, okay, you're SOL, you're not going to get that functionality. Right? But if you do specify a comparator for elements of type T, CMP, then I can use it. Once I've got a comparator, I have something that I can ask things to. Is this it? Nope. Is this it? Nope. Is this it? Yep, that's the one. Right? So how would that look? What we did was, here it is, index of. I'm going to cut and paste this, given this key element. Now, if you never gave me a comparator to begin with, you didn't call the right constructor, jabroni. Right? We're not going to, I don't know what that means. Right? Right? So we'll throw it back at them. Otherwise, I put my logic here. I need to find the element that matches that key. This.cmp key and the ith element. If that's equal to 0, then I return I. Right? Otherwise, if it's something negative, well, nope, the key comes before that element. If it's something positive, that means the key comes after the element. If it's 0, that means that the key and the ith element are the same, and so, well, that's the index that I was using. Okay? That means that I need to write a loop for int I equals 0, I is less than this.size, I plus plus. Right? The ith element here, I can't go with array sub I like I did with the other example. Instead, I would have to do what? This dot get element at index I. And now what happens if you don't find it? The contract that I made over here was an unsuccessful search results in a -1. Why would a -1 be a good flag variable to indicate that no such element exists? That's definitely not a valid index. Right? Okay. What are you complaining about here? Oh, sorry. CMP dot compare to. Compare, sorry. There. Now, we don't have enough time to fix this. It definitely works. I'll show you here. Int index of 42. Did I put 42 in there? Yeah. Is L dot get index of, sorry. The element 42. And then index of 42 should be, I should expect what? 0, 1, 2, 3. Ah. I didn't call the right constructor. I'm a jabroni today. Right? But trust me, we don't have enough time to write it, but trust me that it works. But at the same time, there is still an underlying problem. Right? What am I doing? I'm naively calling this get element at index. So if there are 5 elements in there, conceptually what you should do is you start at the front. Is that it? Nope. Is that it? Nope. Is that it? Nope. Is that it? Yes, that's it. But what we're actually doing is start at the front. Is that it? Nope. Okay, start at the beginning again. Is that 1, 2? Is that it? Nope. Okay, start at the beginning again. 1, 2, 3. Is that it? Nope. Start all the way back at the beginning. 1, 2, 3, 4. Is that it? Yep. Do you want to be that naive painter? If you're getting paid by the hour, be that painter. If you are paying the painter, you don't want that painter. Right? So we'll go ahead and finish that up next time.